Welcome to the movie about Newton's third law. We'll start by looking at a little experiment. You see here a collision card from Pasco, and the collision card has a spring on it, and when I push this button here, the spring comes out, so I can exert a force on another object, which I will do, of course, and the second object will be a same Pasco card which has the same mass. Now, when I push the button and hold one card, it will push the second card away. But now I'm going to try to push that button without holding the card. So I have to touch it very shortly, and I will use a little stick. If first the cards will stand still, of course. Yep, he's standing still. And now I grab my stick and touch very quickly the button, so I do not hold the card anyway. And up. And what you see? Both cards go away from each other with the same velocity. Now I switch cards to show you that it's not just one card, there's also a spring. I turn it around, and I turn the other card around. And as you will see, I try the same thing. I push the cards together, push the button, up, and the cards drive away from each other at the same speed, each in its own direction. So, when one object exerts a force on another object, so object 1 exerts a force on object 2, object 2 simultaneously exerts a force equal in magnitude and opposite in direction on object 1. So, for example, also a boxer, he punches the face of somebody. So the boxer punches the face, he exerts a force on the face exerts a force on the boxer's hand. But of course the hand is much more solid than the face, so the result will be a bit different. A car that drives, the tire pushes the ground backwards, but of course the ground does not move, and the ground pushes the tire or the car, resulting from this, forwards. Think about the situation on ice or in mud, and you'll realize that it's the same situation but different effect. Now let's look at a special situation, or some situation people might think about wrongly. Is here a vase on a table, and we have two forces on the vase. We have the normal force, the table pushes the vase upwards, and we have the gravity force which pulls the vase to the ground. Now both forces are equal and opposite, and they cancel each other out because the vase stands still. Now, but this is not the case with action-reaction forces. Those are also equal and opposite, but they do not cancel out. When I punch your face with my fist, it will not cancel out. Because these two, normal force and gravity, do not form an action-reaction pair. Because they work on the same object. It are two forces on the same object. And remember, it was object 1 on object 2 and object 2 on object 1 with an action-reaction pair. So let's look which are the reaction forces here. Well, the reaction force of the gravity on the vase is the force with which the vase attracts the Earth. The Earth attracts the vase attracts the Earth. The results are different because the mass of the vase is much smaller than of the Earth. And with the normal force, the vase pushes on the table pushes the vase upwards, and the vase pushes on the table downwards. Is the force with which the vase pushes on the table. It's called its weight. Weight in the meaning as in physics, and we will study that later. Let's look also at tension, the tension force, which is also important in situations with Newton's third law. You see a man here pulling a crate or a box, and the box, he pulls it with 75 newtons. The box pulls also at a man with 75 newtons. We're going to study the motion, so we have to regard the box as a free body, only the box. Study the forces acting on the box. So, same box, but drawn a little differently. We have downwards gravity, upwards normal force, and the tension in the rope, 75 newtons. The normal force and the gravity cancel each other out because there is no acceleration in vertical direction. Look at it this way. And don't forget, normal force and gravity are not always equal, as some people might easily start to think from this situation. Normal force and gravity are in this situation equal because there is no acceleration in the vertical direction. Ergo, normal force and gravity equal. And let's look at this with an example. We have Max and Hannes are standing on a skateboard next to each other, skateboards on one line. Max pushes Hannah, so both move away from each other. Calculate Hannah's speed when you know that Max has a mass of 75 kilograms, Hannah 50 kilograms, and Max obtains a speed of 2 meters per second in the 2 seconds he pushes Hannah. Given the mass of Max 75 kilograms, mass of Hannah 50 kilograms, the initial speed of both is 0, the velocity of Max is 2.0 meters per second, and the time is 2 seconds. And we are asked to find the velocity of Hannah. Solution: we use our kinematic speed formula, which gives the speed of Max is the acceleration of Max times the time plus his initial velocity, which is easy. Initial velocity is 0. We rework the formula to get the acceleration, and we fill in velocity of Max is 2, the initial velocity is 0, and the time is 2 seconds, which gives us an acceleration for Max of 1.0 meters per second square. If that's his acceleration, we also have his force. Second law of Newton, the force on Max, or the force from Max, is his mass times his acceleration. 75 kilograms times 1 is 75 newtons. This is the force on Max, but this is the same as the force on Hannah, because they are an action-reaction pair. Which means that Hannah also can use second law of Newton with this 75 newtons, but this gives her an acceleration of 1.5 meters per second square. In the same kinematics formula gives that her velocity equals her acceleration times the time, multiplied with the time, gives the velocity of Hannah is 1.5 meters per second times 2 seconds, gives us 3 meters per second.